Hello, in this session we will learn about some partial differential equation. Next.
यहाँ से कर सकते हैं क्या आप तो यहाँ से लेंगे इसको
हाँ.
वाला बीच वाले
So contents of this lesson are introduction to PDE, formation of PDE by elimination of arbitrary constants, formation of PDE by elimination of arbitrary functions, solution of first order linear equations, non-linear equations, and last method of separation of variables. So first we classify partial differential equation. The partial differential equation corresponding to a physical system can be formed either by eliminating the arbitrary constants or by the element arbitrary functions from the given relation. The physical system contains arbitrary constants or arbitrary functions or both. Equations which contain one or more partial derivatives are called partial differential equations. Therefore, there must be at least two independent variables and one dependent variables exists in partial differential equation. Let us take x and y be two independent variables and z to be the dependent variables. Now the order of PDE we define as the highest partial derivative exists in the equation, and degree of PDE is defined as the highest partial derivative in the equation is called degree of PDE. We use some standard notation in partial differential equation. Del z over del x is denoted by P, del z over del y by Q, del square z over del x square by R, del square z over del x del y by S, and del square z by del y square by T. Now we form partial differential equation in two ways. First by elimination of arbitrary constants and second by elimination of arbitrary functions. So solution of partial differential equation, let us consider a partial differential equation of the form f of x y z p q equal to 0. If it is linear in p and q, it is called linear PDE. If it is non-linear in P and Q, it is called non-linear PDE. Now we consider a relation of the type f of x, y, z, a, b equal to 0. Then by eliminating the arbitrary constants a and b, we form partial differential equation of the form f of x, y, z, p, q equal to 0, which is called a complete integral or complete solution of the PDE. A solution of f of x, y, z, p, q equal to 0 we obtain by giving some particular values to a and b in the complete integral. It is called particular integral. Now we define linear partial differential equation of first order. A differential equation which involve partial derivatives p and q and no higher order derivatives is called a first order equation. If p and q have the degree 1, it is called a linear PDE of first order. Otherwise, it is called a non-linear PDE of first order. For example, px plus qy square equal to z is an example of linear PDE, and p square plus q square equal to 1 is an example of non-linear PDE. Now, important equation, Lagrange linear PDE, a linear partial differential equation of order 1 involving a dependent variable z and two independent variable x and y, and is of the form pp plus qq equal to r, where capital PQR are some functions of x, y, z, is called Lagrange linear PDE. We solve this equation by considering an auxiliary equation of the form dx upon p is equal to dy upon q, equal to dz upon r. We solve this equation in two ways, by using some method of grouping, and second way by method of multipliers, and we obtain two solution. Then we get complete solution of the equation pp plus qq equal to r. Now nonlinear PDE we categorize in four models. First model, f of pq equal to 0. Second model, f of pqz equal to 0. Third, f1 px equal to f2 yq. And last, Clairaut's form. Now first type of equation, f of pq equal to 0, we consider the solution is of the form z equal to ax plus by plus c. Now del z over del x equal to a and del z over del y equal to b. Now putting the values in f of pq equal to 0, we get solution f of a b equal to 0. And if we write f of a b in terms of a, then we get solution b equal to phi a, and its complete required solution is obtained by z equal to ax plus phi a y plus c. Second model, f of z pq equal to 0. In this equation, first we consider solution u equal to x plus ay, then p equal to dz upon du, q equal to a dz upon du, and the partial differential equation is reduced in ordinary differential equation, and by solving it we get the required solution. Now third model, we consider f1 px is equal to f2 yq. First we assume f1 px equal to f2 yq equal to a, and now f1 px equal to a is equal to p, and f2 yq equal to a, that will equal to q, and we know dz equal to del z over del x dx plus del z over del y dy. Then this will equal to p dx plus q dy, and dz equal to psi 1 x dx plus psi 2 y dy. By integrating this, we get the required solution. Now in the last we will discuss method of separation of variable. This method involves a solution which breaks up into product of function, each of which contains only one of the independent variable. Suppose we assume solution is of the form z equal to xx yy, where capital X is a function of small x and capital Y is a function of small y. Then del z over del x is equal to x dash y, and del z over del y equal to x y dash. Putting these values in the equation, given equation, from which we can separate variable, and by using standard method we solve the equation for capital X and capital Y, and we use this method for solving heat equation, one dimensional wave equation, which we use frequently in engineering problems. Thank you.